Welcome to Newton's third law of motion. We have been talking about the first law, the second law, now we are on to the third law, the tricky one, or as Gollum would say, tricksy one. Newton's third law, you actually have heard it in a pretty common form, I'm guessing. Every action has an equal and opposite reaction. And that's how people often think about Newton's third law. But what the heck does that mean? What does that really mean? So this is a law about forces, and again, every time you hear the word force, I want you to think it's an interaction between two objects. Equal and opposite reactions. So forces are interactions between two objects. So a force is object A on object B. An interaction between those two, and what Newton's third law really means is that the force of A acting on B is equal and opposite to the force of B acting on A. That's really what Newton's third law is saying, that the force of me pushing on the wall right now is the same as the force of the wall pushing back on me. Size is the same, but I'm pushing this way and the wall's pushing this way, opposite directions. That is Newton's third law. It is often mistaken for the second law, particularly in places where things are at equilibrium. But what I want you to keep in mind is that on a single force diagram, so if we do a force diagram, what are we drawing? We're drawing all the forces that act on the object. All forces that act on, let's just say, object A. So when we have a force diagram of object A, that's all the forces that act on object A. We never do what A does to other things because we only want what A feels, what A has acted upon it. And so a single force diagram, one force diagram or free body diagram, cannot ever, big word here, cannot have any Newton's third law pairs. Oh, let's just go N3L. That's my standard, N3L pairs. A Newton's third law pair is just this thing right here. It's the force of, well, I'm standing here right now, the force of me pushing down on the floor is equal and opposite to the floor pushing up on me. Me on floor, floor on me. That is a third law pair, a force pair. When I push on the glass, I push on glass, glass pushes on me. That is a third law pair. A single force diagram cannot, ever, can never have any Newton's third law pairs because of this. A force diagram for object A is only the forces on A. The third law pair is a force on B. So Newton's third law pairs are never on one single force diagram. So if I have a force diagram, what should we do? I don't know, do I have anything interesting to think about? I'm standing here. It's not very interesting standing still in front of a camera. How about a roller skater? Let's do a roller skater going this way, all right? So what forces act on the roller skater? Well, we've got the normal force of the ground supporting her, reacting. We've got the earth pulling down on her. And then what else do we have? This is kind of sneaky, actually. I like this. What is propelling her forward? What's pushing the roller skater forward? You might say, well, the force of the skater, the force of the skates. Well, she and the skates are one object, and you cannot lift yourself up by your bootstraps. So it's got to be an interaction with something outside of the skater. So what is actually pushing her forward? What physical object is pushing her forward? Well, if she were in the air, she couldn't do it, which suggests to me that it's something about the ground. And in this case, it really is the ground. It's the force of friction pushing her forward. And this is a perfect example of Newton's third law. When you're walking, so if you're walking, what you're trying to do with your foot is you're trying to push the ground that way. Your foot's trying to slip that way when you walk forward. A third law pair, okay, so I'm trying to push the ground that way, which means that the ground is pushing on me this way. So what propels her is actually friction. Her feet are trying to slide backwards like that against the ground is pushing her forwards. That is a third law pair. So for every force, there is a third law pair, because a force is A on B, which means there has to be an equal and opposite B on A. So for every force, you should be able to think about what is the third law pair. But they never go on this force diagram. So the third law pair for the normal force is the force, let's see, well, the normal force is the ground pushing up on the skater. So it's the force of the skater pushing down on the ground. That would be the third law pair to that normal force. The friction force, well, again, friction is the ground pushing her forward, so the third law pair is the force of the skater pushing, let's see, equal and opposite, pushing that way on the ground. And we get to the really interesting one, weight. The weight of a person is the pull of the earth on them. So it's the earth pulling down on the skater, which means that the third law pair is the force of the skater pulling up on the earth, which is really cool and weird if you think about it. But yeah, we are all pulling upwards on the earth at the same time the earth is pulling us down. So this is an example of the third law pair for each of these forces. But none of these would be on the skater's force diagram because they're all the force of the skater acting on something else. This third law pair would have to be on the force diagram for the ground. This one would have to be for the force diagram of the ground. This one would have to be on the force diagram for the earth. And so third law, equal and opposite. For every action, there's an equal and opposite reaction. Force of A on B, equal and opposite to B on A. That's really what the third law is talking about. And here's some examples. And some people call them third law pairs. Some people call them force pairs. It doesn't matter, it's the same thing. It's just flip the two objects over and change the direction to be opposite. And that's what you've got. That's Newton's third law. So it's a little sneaky, but it looks easy, I know. But it is a little bit sneaky, and when you get to see some questions about it, when you get to start answering some questions, you'll see that you can get it confused with Newton's second law as well. But I hope this was a nice introduction. Good for you for watching. Hi.